Okay? And so this is specifically now, so this is a new type of problem that we've done here, and it's a type of problem where we're going to calculate work. So we're going to start doing problems now where we calculate work, we calculate heat, and then eventually we can calculate the change in internal energy. Okay? So I just talked about how expansion work or compression work can be viewed as exothermic or endothermic. So compression work, right? So if let's say I define now what's inside my piston as the system, okay? Then now this is positive work that's being done. So the surroundings are working on the system for compression. But now, so look at this, fuel explodes. So this is how I know I'm able to define what's inside the system, what's inside the piston as the system. This can be hard at first. How do I get the system and surroundings correctly? It kind of takes some practice, all right? So, but I call what's inside this piston the system because there's fuel that has chemical potential. That's right, we're going to connect all of this. So the fuel that's inside this engine has chemical potential to be used by the system to do work on the surroundings. So now the fuel explodes, that causes an expansion, and so then that's now negative work because the work is being done on the surroundings by the system. Okay? And the equation that we use to calculate that for pressure volume work is P delta V, where yes, delta V, as you might guessed it, being a state function, capital V, which is V final minus V initial. And what I want to point out here is in the case of, let's go through this compression case, okay? So we would say work equals, and I want to talk about this negative sign. Pay attention, there's a negative sign in this equation, okay? And why is that negative sign there? Well, I can rewrite the equation as work equals negative P times VF minus VI, okay? And in the case of compression, we have to think about the initial volume and the final volume and how they're going to be related to each other, okay? So we imagine this initial volume was probably down here somewhere, right? Like I'll draw a little line. And, you know, this is likely what the initial volume was, this whole thing. And so now it's being compressed, so the final volume is smaller, right? So we can say that VI is greater than VF in this compression situation. And if that's the case, if VI is greater than VF, then look what's going to happen. So this VF minus VI will be negative, right? And then times negative P. So negative times a negative gives me a positive. Okay, let me write that multiplying sign better. So that's why we have the negative sign in this equation, because it's just a convention we use. Compression work is positive. Expansion work is negative, and here's why. Negative P times VF minus VI, and then in this expansion, VF will be greater than VI. And because VF is greater than VI, this quantity is positive times the negative sign for the pressure. A negative times a positive gives me a negative. And so that predicts that work will be negative for expansion. Okay, now finally, what about the units? I've got this random unit conversion here because we talked about how work has to be in units of joules. But this formula is pressure times volume, right? So if I use this formula here, so negative sign, and let's suppose I use ATM for my pressure, and I use liters for my volume, which is, it's convenient to do so, then I'll have an atmosphere liter or a liter atmosphere as my unit. And that doesn't make a whole lot of sense, right? But I have this conversion here that says 1 liter ATM is 101.32 joules. It's actually 101.325 joules. Those of you that remember the Pascal unit from gas laws might recognize that number. That's where it comes from. It comes from the definition of a Pascal. But you don't have to know that as long as you know how to use the conversion. Okay? So let's do one sample problem, and then that'll be good for this lecture. Okay? So a tank of compressed helium is used to inflate balloons for sale at a carnival on a day when the atmospheric pressure is 0.99 atm. So I'm going to write that down. P equals 0.99 atm. If each balloon is inflated from an initial volume of 0.0, so we'll say V initial is 0.0 liters, to a final volume of 4.8 liters, so VF is 4.8 liters, how much PV work in joules is done on the surrounding atmospheres by 100 balloons when they're inflated? So let's calculate it for one balloon, okay? And so our formula is work equals negative P delta V. And so that's going to equal negative 0.99 ATM. And then it's final minus initial, right? So that's 4.8 liters minus 0.0 liters. And that's some quick and simple math. So 4.8 negative minus 0 times 0.99. So I didn't do that in the right order, but all the same, it's still going to give me the right number. Okay, and with two significant digits, so that's going to be negative 4.8. And then the units of that are ATM liter. Okay, and I know from my conversion factor that 1 ATM liter is 101.32 joules. Right, so that's how I can use that, right? 1 liter ATM or 1 ATM liter is 101.32 joules. Okay, so now over here I can say, I'll leave the number in my calculator, right, for the best possible answer, times 101.32 equals, and now I get negative 481, and with my two significant figures still, that's going to be negative 480 with only two sig figs, okay, joules. And now that was only for one balloon, right? So I can do this with dimensional analysis by the following. I can say negative 480 joules per one balloon. And I know I can just say 100 balloons, and I don't have to put anything on the bottom right there, because that's just going to cancel the balloons, okay? And so times 100, I probably don't need to do this in the calculator, but I will anyways. Okay, great. So now I get negative 4.8 times 10 to the 1, 2, 3, 4 joules. And at this point, it's probably appropriate to use kilojoules because that's a pretty big number. Even though the problem said joules, that would be the right answer, but right, just to show you, 1,000 joules in 1 kilojoule, so we'll divide it by 1,000. Yep, or so I could say negative 4.8 times 10 to the 4th joules, or negative 48 kilojoules, okay? So the math, we're going to see the math in thermo is pretty simple. It's plugging and chugging into our equations. The hard part is going to be getting the units correct, as well as getting the sign correct. Is it negative or positive? Okay. So keep track of those. So let's see here. Where did